eager to listen to what you
Thank you very much, Mohammed.
4 p.m.
All right, thank you very much for coming to the seminar, and thanks for the invitations again. I think it's always kind of good to be back here in the Maryland and share some of this, the recent result. I'm going to tell you about these studies that going on in the electronics and optoelectronics in this van der Waals heterostructures. Let me start with kind of what I mean by the van der Waals heterostructures. I think probably you heard about a couple of times about this type of story from various different researchers. We've been flooded by this material called the two-dimensional materials, or van der Waals materials, in past probably 15 years or so, ever since the graphene has been experimentally discovered, and there are a lot of study has been happened. Quickly that people start to realize the graphene is only one example out of the host different type of, many different type of the two-dimensional layered materials. Nature provides us materials that can cleavable, meaning that all the chemical bond is within the layer, atomic layer, and atomic layers are stacked by the van der Waals force. Therefore, using Scotch tape or some other method, you can even grow them. And the point here is you can get the really thin atomic sheets, the chemically stable. And yet, this atomic sheet can be very different kind, depends on the choice of your host material. You can get the metal, semiconductors, superconductors, and various different type of things, right? The idea goes beyond that because this interaction between the layers are very weak. In a sense, they don't care too much what's on the top or bottom chemically. So you can actually bring them together, put them together, make the stacks. And if you just choose the right elements of this stack of the material, you can build up the so-called functional heterostructures where each of the components can do the different type of activities, right? So in principle, this can give us some of the design abilities of the putting some of the heterostructures to make this something useful. It's not only just scientific just the goal, but already the engineers, our colleague engineers, start kind of bring up these materials, kind of put them together and try to come up with the various different type of electronic devices and optoelectronic devices and so on. So we know there are implications of the applications based on these 2D materials as well. I'm not going to talk about these stories today, but I'm simply kind of showing this table that emphasizing that as a physicist, also this material start to give us a new platform so we can realize interesting physics. Simply two different dissimilar materials with a different type of the electronic or magnetic or optical properties. You put them together, then create these quantum heterostructures can work as a platform that realize some of the interesting physics there. I mean, starting from very simple things like the p-type and n-type semiconductor, put them together, you get p-n junctions and p-n semiconductor heterostructures, except that in this technology give us that make them really, really thin and atomically thin, such that the quantum mechanics is a basic element so you have to start with. So such a simple heterostructure alone already give us some feeling that one can realize somewhat different heterostructures that cannot be realized in conventional way easily. Right, so that's basically the idea behind of that. And now, that's not only the PowerPoint, and over the years, we know how to create them, at least in the reasonable length scale, about microns or tens of micron length scale, such that we can do somewhat experimental experiments. It's not up to the yet that you can realize it for the real technological application, unless you can grow in the larger scale, but at least you can just do interesting physics studies. The method we heavily rely on is so-called this the core laminations or mechanical exfoliation, followed by the van der Waals stacking method. Method is more or less extended version of the what people can prepare the graphene using Scotch tape. Here, that of course, over the time that we know how to just manipulate and cleave this material in a more controllable way. But the essential part is basically you cleave the material down to monolayers. And using the stacks of the specially designed polymer, you can just pick up the one by one, and you can just make the stacks out of it. And more important part is once you make the stacks, as you see in this cross-sectional TM images, this is particularly graphene encapsulated between the boron nitride. All this atomic interface is super clean. There's no impurities embedded into this between the layer, such that you can make this atomically sharp the interfaces by just kind of this type of method. Particularly, this one is just graphene in between the boron nitride. But as you see in the few examples in the later, we can just extend it into any 2D materials in principle, and a lot of interesting the combination of the heterostructures can be done. So once that you make this type of stack, there's another techniques that we developed in collaboration with Jim Hohn's group at Columbia a few years ago. Is basically selectively etch this the heterostructures, exposing the particular part of this the atomic layer. In this particular case, is graphene encapsulated in boron nitride. Boron nitride acts like the good dielectric, it's an insulator, but graphene is a kind of reasonably good 2D electronic system. You want to make the contact on the graphene in the encapsulation. You can just etch down with the specific chemical the recipes, then expose the graphene, and you just can put the contact from the side, making this covalent bonding between the graphene and this metal. Turns out, although this is just one-dimensional edges, you can make the extremely efficient contact in such a way and create the devices. And has been shown that you can get the extremely high mobilities and very high homogeneity in the sample, and such that allows us to build the interesting devices based on this the van der Waals heterostructure. So that's basically where we are in terms of technologies. I'm going to tell you that probably time allows about 3 stories based on these techniques that I just present, right? So all the stories I select today is basically related with somehow interesting combination between electrons and holes, or more precise, electron-hole pairs that can be correlated in various means. And I have 3 topics I want to cover. The first one is cross-Andreev reflections, where the superconductors can correlate the incoming electron to outgoing holes into the van der Waals system, in particular the graphene system. And once you just bring it to the quantum hole region, you will see that how this correlated electron holes in the quantum edge states can appear in there. Next example is again that correlation between the electron holes, but here that this exciton we form is under the magnetic field across the Landau level. And that's basically the magnetic excitons, and the quantum Hall drag experiments is something I'm going to discuss. And the final the topic I want to discuss is expanding into the other van der Waals heterostructures, especially PN junctions. We want to kind of show you that how one can create this long-lived exciton in the van der Waals heterostructures. Now, most of the results I'm going to tell you today is actually developing stories, except probably the first example I just briefly share. So it is the not well cooked, and many part is just kind of bit of the raw data, and not much of the physical interpretation yet, but certainly I want to kind of share some of the excitement that where we are standing now, rather than just kind of show you some published data. But anyway, let me start with some published data first. So the first story is related with the combination of the superconductor with the normal metal. And there, of course, the well-known physics we know is Andreev reflections. So when superconductor is in contact with the normal conductor, when you try to send the current through this normal to the superconducting junctions, then there is one basic problems we start kind of the encounter is where in the normal conductor, that major carrier is electrons, or maybe holes in the missing electrons in this conduction band. But this electron need to be converted into the Cooper pair eventually inside the superconductor. The way it does, can happen is basically incoming electron form the Cooper pair by grabbing another electron from the normal metals and make the Cooper pairs, but then creating holes in this conduction band. And this hole in the conduction band, if you just think about the current conservation along this direction, should move in that directions, right? So you can create the incoming electron, then create this the outgoing holes in conduction band, and this is what you call the Andreev reflection. And the main feature is, well, basically you expect to see that this retro-reflected hole into the normal metal, right? And this actually explains the many features we are seeing that interface between normal to superconductor. And this electron hole with a certain distance can be correlated such that one can use this as an effect of this correlated electron hole pairs or quasi-particles or Andreev pairs. And often that in mesoscopic physics, the behavior of this correlated electron holes can be quite important. right? Is there a way that we can actually directly observe this reflected Hall? Well, in this geometry is rather difficult because it's exactly tracing back to the incoming electron. However, there has been a way that one can observe this reflected Hall, and that's basically applying the magnetic field. And this experiment was done in the early 80s in Russia. It's Soviet Union back then. It was following way. So it's bismuth. It doesn't have the even low dimensional system. Bismuth has an enormously long mean free path of the electron in the low temperature. And under the magnetic field, basically, when you inject the current, here's a voltage probe. Whenever this cyclotron radius of this electron meets this distance between current injected in the voltage probe, you get this hiccup in your signal. Voltage probe basically pick up the chemical potentials, injected the electron from there. So this first one is basically force of the orbitals, and second peak coming from basically this bounce back with a certain specularity. You get the reduced the peak, but still you get the peaks, and you can even get the third peaks from third bouncing off the smaller cyclotron radius. So as you increase magnetic field, the peaks actually appears. It's reduced because of finite the specularity of the interface, but you still start to see the peaks. What they did in this experiment is basically put the lead onto this sample bound. And what interesting thing happened is when you just cool down the sample such that the lead becomes a superconductor, then they start to see the signal actually, the first signal, the magnetic focusing is still there, but the second peaks actually turn into the negative peaks. And this negative focus signal is very interesting, and that's actually how it works for the measuring this reflected Hall. What happens is then when electron comes in and bounces back from the superconductor, precisely this Andreev, the reflection is happening, and Hall comes out, right? But then Hall will just kind of go through the same path, the cyclotron path, and just arrive here. But Hall carries basically the opposite sign of this chemical potential. That's why you get this negative signals. And this observation of the negative signal actually tells us that indeed the bouncing quasi-particle is a Hall, and we can detect with the voltages, right? Any complaint, objections in this old experiments? Well, obviously, when I just first see these things, oh no, it doesn't make sense to me. And the electron is circulating in this way. How come the Hall is going to the same direction? It has a negative sign of carriers. Now, one thing that we have to notice that is a Hall that created here is not just a semiconducting Hall that we usually familiar with, that creating something in valence band. This is, say, the Hall in conduction band, or the better concept you can think about is a missing electron, right? So Hall, actually, the group velocity of Hall is the same direction as the electron velocity. Another way to think about this is a Hall is a really weird Hall that you create in conduction band, unnatural Hall, which actually has an opposite sign of the charges, but also opposite sign of mass. Mass of the Hall here is negative. So therefore, it actually negative sign of charge, negative sign of mass will make the same direction as electron directions. Anyway, so this is an experiment to beautifully demonstrate that you can measure this reflected Hall. Of course, now one can do very similar experiment in the graphene, especially that I told you that we know how to make the good contact on graphene, not only just normal metal, but also superconductors. So here's a device that made out of the graphene channel, and here's my injectors, here's my current detector, and here's the niobium, the contact we made here, right? With reasonably good engineering of this contact with the niobium, we can create those kind of clean Andreev reflections there. And indeed, the measurement shows that here the negative magnetic field is basically these directions, because if you flip this one, the first peak is basically first focusing peak. Second peak at the 8 Kelvin basically has a positive peaks, although background. But once you get down to 1.5 Kelvin, where niobium becomes superconductor, peak becomes deep, and negative signal appears like similar. So we know that basically we can repeat the same experiments what has been done in the 30 years ago with this bismuth, right? So, okay, so this actually demonstrates at least we can make the fairly transparent contact. We can create the Andreev reflections, right? The next thing we want to do is now, because now we can realize in a two-dimensional electron system, we can ask following things. What if we just increase magnetic field and bring this system into the quantum limits So all of this description, magnetic focusing, is semi-classical physics. We're just kind of moving around wave pockets. But instead of doing that, what if we just kind of bring them into the quantum Hall limits, such that now we just kind of put everything kind of into the edge state pictures. So if you just imagine that what happened in the quantum Hall limits, the following things happen, right? So if I have this is my superconducting contact, now I have this, this is my biasing the electrode that is missing. And this is my voltage probe. So it's a whole bar, but one of the contacts is made of the superconductor, right? And then ask what happens when the reflection is happening in the superconductors. What happens is when you just bias here and drain the current and measure the voltage in whole bar, of course, the electron is coming into the through the edge state, create this the Cooper pairs and make these Andreev reflections. And then this hole is coming on. If you think about skipping orbits, the hole just bounce back again into the superconductor and create the whole Cooper pairs and make the electrons and again and kind of going through, right? So it will just going through the peripheral of the superconductors many times, and every time you create the electron and whole Cooper pairs. If this happens many times, in the end of the day, you have more or less cancellation between the electron Cooper pairs and whole Cooper pairs. And when you just leave it here, basically this is somewhere mixtures between the electron and holes, and likely 50 and 50%, right? So if you just measure the outgoing or the downstream of this edge states to measure the chemical potential, what you see is basically we'll basically averaged out V versus minus V get about the 0 chemical potential, right? So unfortunate part is now if I just bring this focusing experiments in quantum limits like this, we may not be able to see that downstream of this the particle because we start kind of get the mixture of the electron holes throughout this kind of long peripherals, right? However, as you see in the next plot, we can actually change the story a little bit. If we make that this superconducting electrode is really thin. So what happened is that we just can make this superconducting electrode really thin, the chopping off this Andreev conversion process or Andreev reflection process in the following way. So usually the incoming electron, we just collect the electron from the same side of the conductor. But what if that my superconductor is so thin and contact with another normal matter is on the other side, I can grab the hole from electron from the other side of the conductors and create the hole, and this hole will flow the same directions, right? So if we just create those kind of thin superconductor, basically we can create the Andreev reflection is happening in the downstream side, and let hole flow. And of course, hole flow with the opposite chemical potentials of the electron. Therefore, I can just read off the negative chemical potentials on downstream. So that's basically experimental proposed. Can I just make this electrode really thin and thinner than superconducting coherence lengths and create this system that whether we can detect those kind of negative the chemical potential in downstream? Yes, please.
So what happens when you make it? What if you made it shorter?
This one shorter.
No, the first one.
This one shorter. Yeah. Right. Doesn't matter because as long as what is important part is okay. So I would say this is a peripheral length scale, right? Because in this way, that often people call this is what we call the Andreev edge states. Yeah. Basically, this is the skipping orbits that consist of the about equal probability electron holes, right? Yeah. So important part is even if you make this shorter, but if there I have enough the length that I can create many the skipping orbits. Very similar physics will be very similar.
Right, but it wouldn't necessarily average out. It's just fluctuate.
Okay, so of course, if you start kind of reduce down the length scale, right? Then probably yes, I agree. Then you start to get these things. But usually here, the magnetic length scale, which actually is more or less in the quantum limits, close to cyclone orbit length scale. That's scales over the tens of nanometer. So we are talking about really mesoscopic size conductors, which actually go into very similar story like this. In a moment, yeah. So we can even we can make indeed those kind of devices. Here is the graphene device, very similar to before. That now I just kind of rotate into the 90 degrees in counterclockwise, and this is my superconducting contact. But as you see, this is finger shapes, and the width of this finger is something like the 100 nanometer length scale, or smaller than 100 nanometer length scale, matching more or less coherence length of the niobium nitride in this particular case. And indeed, if you just measure downstream potentials here, which actually normalized by the current such that it comes up to the units of this resistance, and this is nu equal 1, nu equal 2, nu equal 6, and that's a typical sequence of the quantum Hall appears in this the single layer graphene in reasonably high magnetic field. You start to see that these downstream potentials go deep below to this zero, showing that we can just detect negative chemical potentials coming through downstream. And this tells us that indeed we can create this Andreev convergence, and we can even detect that. You start to see that this signal is relatively small. It's only about 10% of what is expected signal, which means that the convergent efficiency is probably quite reduced down rather than 100%, but nevertheless, significant amount of the signal tells us that this conversion is really happening, right? And to make sure that this is really related with the previous pictures I present, we can make the finger width larger and larger. So there's a different type of device, D2, D3. As you just increase this width of the finger, that negative signal we just observe is quickly drops down, right? And this exponential decay tells us that the characteristic length scale is about 50 nanometer, which also match with the superconducting coherence lengths expected in niobium nitride. So tells us that indeed we can create those the downstream of this conversion of the hole in this system as long as this finger width is small. So that's nice. Yes?
So you've characterized this as being a negative signal, but
yes.
It looks a lot like it's consistent with zero.
No, yeah, okay. Yeah, I admit that this, yes. Unfortunately, I dropped out all the following slide because I want kind of stuck into the other talks, but I can show you that later. So there are a few tests we can make, right? So if you go to the above the TC, how this signal changes. If you bias it outside of the superconducting gap, how this changes. Every time so you just kind of bring it out, bring the superconductor out from the superconducting state, this becomes really dead on zero. Actually, it becomes positive. The reason it becomes positive is, remember that it's not the four-terminal measurement we are doing anymore. This is basically, we are measuring the downstream of the chemical potentials there. So there's contact contributions onto this lead actually contribute to the positive signal. So I admit that this is a kind of few tens of ohm, right? But we have the reasonable confidence that this is indeed negative, especially if you just take account all this the contact resistance on this part, right? So I can show you that later in this separately. But this is a nice demonstration, but actually there's a kind of new spins that tells us kind of what direction we can move on here, right? So there's a kind of slightly modern way to interpret the same data, and this is the following way, right? So if we just look at this superconductor, this is a very thin, it's close to 1D superconductor because I think this width is correct in the dimensions of the superconducting coherence length. And then you wonder why I actually make this finger shape, so why it's long, right? Because there's a theoretical proposals associated with this. So if you just think about just quantum edge states, to create this finger, first of all, by the way, we actually make this trench, basically remove the graphene and we backfill with this superconductor. So you can think about, without superconductor, basically graphene quantum edges will just follow like this, right? So there's a quantum edge and there's quantum edges. And quantum edge is basically, we know, as a chiral, the 1D states. But then, if you just think about, well, my superconductor is basically coupling this between these two chiral edge states with the superconducting order. And we've been hearing about this quite a lot. That's basically the basic ingredient to create the Majorana states, right? Indeed, and one of the picture is by just kind of coupling these two chiral edges, you can create this Majorana edge states. One especially here is localized, and the other one is probably reasonably localized, probably delocalized. One way you can think about this cross-Andreev reflection is basically those kind of resonance through this Majorana state we can create in this way, right? In fact, this theory even just bring us even further. If you just realize this is not only integer quantum Hall effect where you can create this Majorana states, if you just bring to the fractional quantum Hall state, theory tells us that, well, maybe you can create even parafermions with a very weird non-abelian statistics in the system. So that's basically exciting new direction. Probably you can push along. We actually have the very first step. It's the preliminary data, but I want just to show you. So one way you can prove that is, okay, if it is we create the Majorana states, How do we prove that? We create another one, just bring them close, and create some sort of Josephson junctions between them, and just try to read off their phase and braiding of, and those kind of things is kind of new direction. Indeed, we start create those two finger facing together. We start to see that they create the Josephson junctions, and already that very preliminary data start to show that this Josephson junction, critical current, can be modulated by just quantum Hall states, and that's kind of interesting. So as we just get into the different filling fraction, the conductance of the normal conductance through the system is stepwise changing as reflecting quantum Hall physics. But once you get it to superconductors, and their critical current also follow these steps, and more or less a change of this critical current step is related with the quantum conductance with the gap of the superconductors up to some numerical constant. So this start to tell us that at least we can create these unique particles, and maybe we can create this interaction between them. So that's kind of exciting new directions. Maybe this gives us a new platform to realize interesting, this topologically interesting the species based on the 2D system coupled with the superconductor. Okay. Second example. Now, I told you that that there's another way that I want we can create the electron-hole pairs, and I think this is a more traditional way, I would say. Traditional way that we can create the electron-hole pair is basically in the semiconductor or in the gap system, put the lights and create this electron-hole pair, and by Coulomb interaction, they bound together and make this exciton. Often that exciton is reasonably long-lived, although there's a transient object. And all those kind of electron-hole pairs, they govern a lot of important property, a lot of important optical property of the solid. So we know that how to just kind of understand this optics in conventional condensed matter physics languages. One issue here, though, is exciton is always a transient object. It's not the ground state properties. It's the excited state of the material. So depends on the material. It can be very short-lived. But imagine that if you have the long-lived exciton, and we can just kind of think about that as a quasi-particle or composite particle, we can ask what kind of statistics this exciton will follow. Of course, exciton is constituent of the two fermion, electron and hole. So their spin must be integer. Therefore, it should be boson, right? But then, as a boson, if you create a lot of exciton, and if they're long-lived, they may actually create many-body quantum states, such as the exciton condensations and those kind of power, right? Problem that we have here is that usual exciton is short-lived, so we want to create something long-lived exciton. One way that in semiconductor industry or semiconductor research has been worked it out is make the exciton long-lived by separating electron hole in spatially or in momentum space, such that they're suppressing their recombination, right? Here's a good example. If you make this semiconductor heterostructures and tilt the semiconductor heterostructures by biasing it, often that creating this so-called interlayer, that one electron is one layer and hole is another layer. This is often called the interlayer exciton formation, can be stabilized. And once you create those kind of interlayer exciton in semiconductor heterostructures, there has been some report that you can create some of the macroscopic quantum mechanical states. Transient, but nevertheless self-organized, the coherence appears in those kind of system has been done. So that is kind of good motivations we can just adopt from the semiconductor heterostructures and just ask that, can we realize very similar system and excitons and can long-lived, right? By the way, there is actually a way that you can make the exciton as a ground state properties. It's not through this semiconductor heterostructures creating electron and hole by the light, but applying the magnetic field. So let me just kind of starting with that topic first. Imagine that I have the two conducting layer. It can be semiconductor heterostructures. It can be two pieces of the graphene. Doesn't matter, right? So I have the two pieces of the conducting layer, two-dimensional system, and apply the magnetic field. And under the magnetic field, of course, the Landau level forms, right? I can visualize this form of the Landau level is basically a bunch of the cyclone orbits is occupying in my sample, right? And imagine that I just kind of partially occupy this Landau level in both of them, right? Once I just fully occupy this Landau level, each of the Landau level will develop the quantum Hall states. And then current will flow through only the edges. But once you have this partially filled Landau level, meaning that only just kind of partial number of the cyclotron orbit got occupied in the both of the layer, it is just kind of bad metal, right? I think it's conducting, but it's a weird metals, and it's basically not a good metal, but it's just a dissipative system, right? However, I just kind of put just these two Landau level or two layers in such a way, as an individual layer, they are partially filled, but as a total, they are full Landau level. In other words, I just fill this two layers in compensating way, such that if I just induce grab the more all of the electrons there, it can fill up at least one of the level, right? And visually, what it look like is following things. If I just kind of bring them close of this two layer, what will happen is then electron in the top and electron in the bottom start to see each other. And when you just bring them close enough, then there is the exchange interaction start happens, right? Which means that Pauli exclusion principle start kind of kicks in. What does it mean is that actually electron that underneath of this bottom layer will start to avoid the electron from the top layer. And that energy scale is basically Coulomb energy scale, mediated by the exchange interactions. So if I just put them really close by, then you can imagine that all the electrons in the bottom layer will avoid each other since we just put them in the compensated way. So you will see that as this distance becomes smaller, you will see that there is a perfect correlation between top and bottom layer will happen. One way you can view that is you just kind of make the projection from the top and just look at it, right? If you just put the D very small, this is what will happen, right? And as a whole Landau level, if I just project it, this is a kind of complete field Landau level, which means quantum Hall effect wise, well, I expect to see that there is an edge state happens and it should behave like this, the one single Landau level of the quantum Hall states, right? But of course, in microscopically, if you just look at them, they are small separations, and then basically the bunch of the dipole should be there. Electron holes down there. The dipole moment will just pointing out the up and down, but complicated, or mathematical expression is something like this. But nevertheless, as a just coarse graining out, they should behave like the one full Landau level, right? In fact, this experiment was done from the 90s. There's a heroic experiment was done in Jim Eisenstein group at Caltech. They made this quantum bilayer and make the individual contact on each of the layer, and they see the following things. So basically, there are a few different measurements you can do. You can just send the current in one layer and measure the current in the same layer, the voltage in the same layer or different layer. And if you just measure in the different layer, this is often what you call the drag experiments. So send the current and measure the voltage on another layer. If these two layers couple, there's something's happen, right? So what they see is kind of quite amazing things. Of course, they have all the quantum Hall effect in individual layers, but when each of the layers about half filled, suddenly something's happened. So if they measured in half filled Landau level, they actually behave like the full Landau level. As long as they are half filled and filled, then the system behaves like again, it's a nu equal 1 quantum Hall states. But even more exciting thing is if you send the current in one of the layer and measure the voltage on another layer, it's a drag measurement, especially if you measure whole drag measurement, they see the whole drag is quantized as the same quantum Hall quantizations. And showing that these two layers are kind of completely coupled together. This is quite the exciting part. And later experiments they actually showed is also if you just measure the one layer in the one direction and measure the other layers, so-called the counterflow geometry, they see the perfect conductors. If you send the current in one layer and try to measure another layer, there is a perfect current drag in the opposite direction is happening. So there is some sense that this is some sort of superfluidities of the system happens. So that one of the interesting interpretation is indeed you have this magneto-exciton forms under the magnetic field across this the Landau level, and these magneto-excitons condense into the superfluid and created the superfluid states of the magneto-exciton is interpretation of the seminal experimental data that they have. Of course, we can do the very similar thing into the graphene, right? Again, that replacing the gallium arsenide heterostructures with graphene, make the contact of the individual layers, and we have the top and bottom the gates. Unlike the gallium arsenide, we can actually have the huge tunability of this gate to create very similar experiments. Not surprisingly, we see the very similar result when we just measure the individual layers. We have the nu equal 1, nu equal 2. The signature of fraction is also appearing. But the important part is when they get into the half-field Landau level, very similarly, that the quantum Hall effect becomes a re-entrant. But at the same time, if you measure this drag hole is quantized is the same value, indicating the very similar experiment as the gallium arsenide case actually happened. So not surprising, as long as this physics is general for any 2D system under the magnetic field, this is what is happening. What difference in the graphene is, of course, compared with the gallium arsenide, energy scale is much higher. This is expected in a sense, because if you put this graphene and two graphene layers together, you can just put them together very close by, only 2 or 3 nanometers away. So you can think about electron hole can be really close by. The binding energy is strong, right? So all the energy scale becomes stronger, such that this exciton formation will readily happen. The condensation is happening. So unlike the gallium arsenide, where you can only see this 100 millikelvin ranges, this experiment can be seen even 10 Kelvin ranges. You start to see that signatures of this exciton condensations. What is a more exciting part is we can also repeat very similar experiments in gallium arsenide. In here, that we can just send the current from the top layer, but then we just reconnect that from to the bottom layer. I think this first experiment was done Ian Spearman here in gallium arsenide, but we just repeat a very similar thing in the graphene. But then you just kind of measure the voltages in this layer or that layer, doesn't matter. So basically, we want to kind of see that whether there is any dissipation component in this configuration. This is half-field Landau level. Without this, if you measure just kind of dissipation there, the drain there, you get huge dissipation. But once you just return this and drain from there and measure dissipation, that dissipation is gone when the magnetic exciton condensation is happening, right? So it tells us that indeed feeling of the superfluidity is happening there, right? Another important part is actually in graphene, since we can tune this the density in wide ranges. Unlike this, the effect is seeing only half-field Landau level in gallium arsenide. We can see that it happens on the many different Landau level. For example, in this particular case, is a bilayer graphene to the bilayer graphene. And we see that the nice drag effect appears half-field Landau level, but also the same thing happens for half-field Landau level and the 2.5-field Landau level. As long as this Landau level has a right symmetry in the system, we can always create those kind of drag effect. This is a two single layer. This is most recent experiment with even higher quality because we start to use graphite backgate and topgate, and you start to see that that this is a drag signal, and I can highlight a few parts, and this is nu equal 1, nu total equal -1 and 1, total equal 2, 3, and whenever there is the signature of the drag signal appears, if you zoom in, you see the very similar, the quantized Hall drag appears. We know that the effect, the magnetic exciton condensation happening. And for example, here that nu total equal 1, if I just cut it through, that when the two Landau levels are filled in compensatorily, that you start to see the important part is that, what is it? Okay, so drive and drag and everything's more or less go to 0 in here, and the whole drag and whole drive actually goes to the right values, the quantization. So we know that it actually happens for any cases. Now, the real story that I want to tell you is now, this is background, but following. So let's zoom in one of the states here. For example, nu total equal -1. And although very similar physics can appear in other places. I want to measure the counterflow drag. And that's basically, as I said, I'm sending current in one direction and returning to another directions and measure the longitudinal resistance. That's a counterflow resistance XX component. And you can also measure counterflow XY component. But let's focus on XX component. I painted the pictures that if the magnetic exciton condensated, it's actually viewed as a superfluid, right? And one of the evidence is that this quantity goes to 0, right? So I want to use this counterflow XX as my experimental tools, whether there is a superfluidity happens or not. That's basically experimental observation. So if this goes to 0, that's a superfluid. If this is finite, I know the system becomes dissipative, right? And then I showed you that happens in low temperature and high magnetic field. But we can ask that, what happens if I just try to do this in the different temperature and different magnetic field, right? So I can just draw the following phase diagram. So this phase diagram is constructed in the following way. I control the top and bottom gate voltages such that as we tune the magnetic field, I try to stay on always both of the layers half-field Landau level, right? So of course, as you increase the magnetic field, I have to increase my gate voltages, increase the density to make that, but assume that I'm doing that, right? And just measure the counterflow XY, and just record that. And then I just change the temperature also, right? And this bluish region and dark blue region, this is basically where counterflow XX goes to 0. So I know that, okay, so as it should. I'm seeing that there is some superfluid condensation is happening there, right? But as you increase the temperature, well, then eventually this becomes a higher resistance, something like the 20 kilo ohm. Basically, this becomes a bad metal, as I said, turn into this bad metal. In other words, condensation is breakdown at high temperature, which is also expected, right? But you start to see that, have the feeling that, okay, so that's not how it breaks it down as interesting shapes here, right? So it's like the dome-like the shape as you change the magnetic field. And you start to see that roughly, here the change is gradual, but change is sharp. I can show you that a little bit more details there. So I call that this is condensation phase, and this is normal phase, and it's this kind of phase transition is happening with different behavior. And if I just kind of cut through different the constant magnetic field and temperature behavior, this is behavior, right? I say this is gradual, which means that this blue line is gradual. This is a rather stiff, sharp changes. Almost look like superconducting transition, right? Finite conductivity, the resistance drop down to the 0 suddenly, right? And something is in the middle, right? In fact, if you just plot this one in the RNS plot, you start to see the interesting. Low temperature, low magnetic field behavior is more like the activating behavior. In fact, this is what has been seen in gallium arsenide. When you look at this counterflow or any of this kind of experimental order parameter, they're always activating, right? So that's not surprisingly, we see the activating behavior, but as you increase the magnetic field, you start to see the activating behavior becomes worse, or you can see that even just the two slopes or whatever, right? But sharp transitions. But certainly something is happening, kind of change is happening, and there is an interesting phase boundary we have to understand this type of things, right? So this part of this, the experimentally observed phase boundary immediately actually evokes very analogous pictures we have seen in other systems. I just borrowed this slide from the Ogawa's talk. It's actually that phase diagram that sketched for the real excitons and exciton condensation. Or of course, for the real exciton, if you just put a lot of excitons start to screen each other, such that exciton becomes unbinding, and that's why we call the mode transitions. So if you have the exciton gas, if the too high density, basically exciton gas will dissociate with electron hole plasma. Now, if you just think about those kind of exciton system, if you cool down low temperature enough, then of course exciton as a boson can condense into the Bose-Einstein condensation of the excitons. But electron hole plasma here, well, if condensed, if it's in the right condition, it may actually condense into the superconductivity and separate the electron holes, right? So there is a kind of BCS type of superconductor happens. And in fact, the theory tells us in this system, maybe there is a smooth crossover between this BC and BCS on this exciton system in the low temperature. And there are some things that developed in this line, although experimental observation is already controversial in these directions, right? Very similar analogy actually can be applicable for the magnetic exciton I was talking about, right? The theory is a little bit more complicated, but you can more or less see the important part is here that this theory is governed by the two important length scale. One is what is exciton size, the bore radius of the exciton, and versus what is the distance between the exciton. Because if this distance is large enough with the bore radius, exciton is well separated, we can just view as exciton as individual quantity. But if you increase exciton density such that bore radius versus this exciton distance becomes comparable, then exciton is not a good quantity anymore. There's screenings and all of these things, right? Very similar way, if you just describe the magnetic exciton in a similar way, the important two length scale is one is distance between the layer, which actually determine the exciton size. Exciton distance is governed by the magnetic length. Basically, by tuning the change in magnetic field, you can tune this distance of the exciton because that's basically distance between the guiding center of the cyclotron orbits, right? So very similarly, we can see that D versus D, which is fixed by the experiments, versus LB, magnetic length scale, which actually change tunable by magnetic field, will play an important role, and we can actually tune over this type of this the interaction between the excitons, right? Indeed, if just kind of look at my experiments that I showed you here, you can do the following things, right? In this, when magnetic field is small, in other words, the magnetic length is long, in this D over LB, D is much, much smaller than magnetic length. What you see here is a smooth transitions, and that's where that I get this activating behavior. As you increase that the magnetic field, L becomes small and becomes comparable, you start to see this activating behavior start to spoil, right? One way you can just do that is just to draw that how the activating energies, if you just get the slope, got changes as a function of magnetic field. Low magnetic field, we have the really well-defined, the activating behavior. As you go to the high magnetic field, you start to see that there are multiple slopes appears. The dive kind of spread it over, although that maximum slope is following through this similar line. And you can even just do this experiment with a different thickness of the layer, and you can nicely kind of extend this curve. But nevertheless, we start to see that activating behavior is what is governing in these ranges, but that got changes, right? I mentioned that high field, there's a stiff changes of the resistance, right? Or counter flow resistance, almost like the superconducting transitions. In fact, actually, it's funny that if you just measure carefully IV characteristics, so send the current and measure the voltages, and these IV characteristics precisely follow the Pauli's law at the low temperature, and as you get, or at a low bias, and as you increase at the high bias, it becomes ohmic behavior. In fact, there is a sensitivity change with the temperature, and all this behavior of the IV, anyone working the 2D superconductivity immediately notice that, this is IV for the 2D superconductors where KT transition is happening. Indeed, precisely that IV characteristic we're measuring can be described the KT type of the transitions, the power law behavior IV, and from there, from this experiment, we can extract this KT transition, costless, Dowless transition temperatures, and plot it out. Nicely actually scales with the D over L in proportional to the magnetic field scale, right? So we start to see that a lot of things that we just seeing can be framed in terms of this superconductivity or superfluid type of the transitions as kind of indicating from these pictures. So I don't have a lot of time, and this is a kind of brewing story, so I don't want kind of definite term, but roughly the experimental observations start kind of propose the following things, right? So basically, as you change the magnetic field, that we just going through this one regime to the other regimes, right? More like that there is some crossover or behavior changes. This strongly suggests maybe we are getting to this BC type of regime where the exciton is well separated and well described by the individual exciton, to the where that in this the magnetic length is small, such that all the exciton is basically all intermingle, where the exciton picture is not good. There must be some behavior changes seen in our experiments. The other one is temperature dependence, strongly indicating indeed, at least in this high field limits, there's a kind of clear behavior of this KT type of transition is happening. So whatever order parameter it is, that indeed it is two-dimensional system, and it's condensation phase. So getting out from this condensation phase, basically observation of this KT physics is rather natural things we are seeing. Of course, this is not all, and we have a lot of the unsolved problems here, and probably what is the origin of this activating behavior. Might be there is a kind of some sort of Majorana type of physics. If you just think about this is 2D XY models that in the limits of the SU2 symmetries in D equals 0 limits, that's maybe natural things. Or maybe the other one is what is the real nature of this BCS limits of the ground states in this one. How they create the KT transition. There are some of the theoretical the predictions there. I don't know that how well they are matched with this experiment at this point, but certainly this is kind of big open questions we are facing in here, right? So I have probably 5 minutes that quickly go over the last project. Now, everything so far I just mentioned is involving the graphene, but in the beginning I just mentioned that graphene is only a good, but one example of the 2D system. In fact, there are the series of the 2D materials, especially semiconductor, we call the transition metal dichalcogenide. It consists of chalcogen atoms surrounding that the metal that usually is the tungsten, the moly, and those kind of things. Then it becomes semiconductor. This material, just if you just look at the projection, it looks like more like the graphene, look like the structures, or more like the boron-like the structures. The inversion symmetry is broken here. But also on the top of that, there's a strong spin-orbit coupling because it contains the heavy metal. Will make this spin-orbit the band structures is spin splits, right? In the end of the day, what you find is the conduction band and the valence bands are gapped at the Brillouin zone corner, and also they are spin split. Because it's the band at the Brillouin zone corner, the value index is very good. So K and K prime index is a very good way, and they can be optically addressed because you can use a circularly polarized light to address one value versus the other. But because they are also spin polarized, which means that using the optics, one can address the spin of the system. So in that regard, there's a lot of excitement. Maybe if you tame these materials, one can use the combination of electronics and optics and realize some of the quantum operation onto the system. Furthermore, because of this is so thin and all this electric field, when you create the electron hole pair or the excitons coming out from the materials and just in principle go through the free space or some dielectric. So if you just choose your dielectric and free space right, there you can minimize the screening, Coulomb screening. In other words, your exciton becomes strongly bound. So indeed, experiment actually tells us that you can create the strongly bound excitons. And because exciton is strongly bound, you can also use, you can attach another charges on excitons, the so-called the trion, can be stabilized. And one can use not only just a neutral object, but this charged exciton, you can just create it and manipulate in the system. And there are, in the field, there are a lot of reports such as not only excitons or trions, biexcitons, and they are stable. They can be manipulated by circularly polarized. It's Tony Hines group's result, Xiaodong-Xu's group's result. They all report that there are a lot of interesting optical properties one can manipulate in the system. As the transport group, what you can do is we can actually make the device, electronic device, and combine with the optical properties and measure these things. So this work is in collaboration with Hong Kong Park's group and Michelle Lukin's group at Harvard, basically showing that once you make the device, transistors, and we have to put the gate, you can just not only do the transport measurement, but you can just do the optical spectroscopy as well. Here is, I'm showing you the photoluminescence spectroscopies as a function of the gate voltages. In particularly in here that we have the two gates, which means that not only I can control the density, but also I can control the electric field in the vertical directions. And that's important because the field is readily coupled with excitons, right? The result is interesting. Here that in this plot, this is the energy scale of the photoluminescent, and the bright red is basically peak of the luminescent, blue is background. What you see here is when you put the zero density, in other words, when you put the chemical potential in the gap, you see the multiple peaks. So here's 1, 2, 3, or maybe more, right? So you can assign this is exciton, trions, and other trions. Depends on this, all this sample preparation. It has been worked it out quite well before. But then when you apply the gate voltages such that you start to change the density in the electrons and holes and all this, the optical spectrums got modified, right? Especially exciton will quickly dies off once you drag out from the gap region, because now everything becomes screened by electron and hole, and that quickly becomes a trion type of the peaks. And their energy got modulated as it should, right? Because the screening property got changes. But what is interesting is following graph. Here, that we apply the electric field in the vertical direction by charging top and bottom voltage, gate voltage into the opposite polarity, right? And fix the density. And then what you see here is that the intensity got modulated, but exciton and trions, their peak position doesn't move as you change the electric field. And this tells us immediately optical transition dipole moments of this optical species we created is all in plane. Therefore, out of plane magnetic electric field will not couple with its energies, right? So it immediately tells us this is a two-dimensional object. Okay, so that's kind of good assurance. But then, of course, we can create this out-of-plane object, or the three-dimensional type of excitons, now by putting these two layers together, right? So if you just put the P layer, N layer together and make the heterostructures, right? You can immediately see that you can create the exciton of each of the layer, but then if you just move the carriers one layer to another, you can create these interlayer excitons there, right? What is the experiment we want to do is basically we want to create those kind of interlayer excitons by optical means, but also we want to control them by electrical means. So we construct a device with the P and N layer together, but then we have to put all the contact in all surround this, each of the individual layer, like the graphene device, but also we have to put this top and bottom gates. So that this is kind of final device shape. It's a really heroic efforts, many electrodes in each of the layers, and the control on the top of that we have the top gates and bottom gates, matching gates. So many control. But in the end of the day, when you just take the optical spectrum, you will see following things. This is only the tungsten diselenide only. This is moly diselenide only layers, where that they own their exciton peaks appear in the photoluminescent. What is the interesting part is when you just look at in the middle ranges, where the two layers overlap, you basically suppress individual layers of optical, the photoluminescent, and get the photoluminescent of the interlayer excitons only. And not only you get these interlayer exciton peaks, they can be modulated by the gate voltages. Very similar way, as you change the density, they got modulated. But more important part is now when you just kind of change electric field in the vertical directions, unlike this the single layer, this two-layer interlayer excitons, they shows huge energy changes, just kind of linear stack effect, tells us that basically exciton is aligned with the electric field we are directing. So we know that this is interlayer excitons. More exciting part is, in fact, that their lifetime is fairly long. Intralayer exciton is only just kind of tens of picosecond of the lifetime. Here that this is hundreds of nanoseconds, almost kind of microseconds long-lived excitons. And this is ideal, again, the electron holes are living in the different layers, right? But the important part is that their lifetime can be also controlled by the electric field. In a sense, by applying the electric field, we can just kind of move the electron hole pairs, actually move further away, and that's basically make their lifetime longer and longer. So we know that their lifetime can be controlled in the very long lifetime. And long lifetime is very important because that's where we can make a lot of excitons. And this is a good example. This is our heterostructure area. We put the lasers there, exciton generated, and they start to spread it over because of their long lifetime. We can see how they actually spread it over. Since time is kind of rather short. And from there, you can just kind of measure what is the diffusion constants of the exciton diffusions and so on. So I think that's kind of good direction. So we know that we can create the long-lived excitons. We see how they actually moves around. One thing that noticed here is you see that that this is a folding edge of this laser pulse, and then exciton does not disappear uniformly, but there are some spots in the sample, as you see here, that inhomogeneity actually appears. So clearly, our sample has a lot of inhomogeneity. We don't know what's their nature, but they are there, and they actually control their exciton dynamics. We believe they are some sort of exciton trap because they are brighter. But good news is once that exciton is trapped, we see that exciton is rather long-lived. So the next level of the idea is, can we actually engineer this exciton trap to make this even longer-lived, and we can have the both control. We don't have yet that stages, but at least that when we measure this exciton density by just looking at the blue shift of the photoluminescent, we start to get the sense that exciton density is something like the 10 to the 11 exciton per square centimeters before we heat up the samples in substantial level. And that's important because this exciton density is exactly tells us how much actually we have to generate exciton and what is how low temperature we have to go to create this exciton condensation. According to this mean field type of the simple calculation has been done onto this interlayer excitons by the Fogler, we are around kind of these regimes. So we are not yet this condensated regimes, but it's not too far. So the further engineering of this exciton to make this a higher density and long-lived is important, and we believe that by engineering tools we can just do that. Time is really up, so I don't think that I want to go over to details, but it turns out that we can not only generate the exciton by the optical means, but since we have the contact by p-n junction, we can create the exciton in the electrical means, electrically generated exciton. They are also long-lived. But also, more important part is that, let me stop in almost this slide. We start to actually put the gate, local gate, and we start just to demonstrate that indeed we can just move around this optical species, Tryon, for example. To create the exciton traps, we have to create the dielectric traps, but this is already a demonstration. We can start kind of engineers optical species in the kind of several locations, something like that, demonstrate here. All right, so let me just quickly summarize. So I just try to tell you about the three episodes of the electron and hole pairs in here, right? So using either superconductor or the quantum or bilayer or real p-n junctions, there are kind of demonstration we can create these excitons or the electron pairs that can be strongly correlated. But the important part is each of them actually start to provide us some new platform to realize interesting physics. For example, this correlating hole pairs may actually going for the new platform to the qubit type of topologically protected qubits ideas, or some of the other exerting many-body states and so on. So I think this is, in a sense, a very exciting field in that regard. All right, so my final thing is I want to really thank my collaborators. Without collaborators, this never worked, and my students and postdocs who actually did the work. The first part I just mentioned, the cross-Andreev reflection, was done by the Gil-Ho Lee, who is now in postdoc, in collaboration with also Ami Yakubi's group. Magnet exciton was done by the Xiaomeng Liu, in collaboration with the Corey Dean's group at the Zia Lee is actually co-contribute. And theory-wise, we got a lot of help from Bert Helferin. And Interlayer exciton was done by the Luis Haregi in collaboration with the Michel Lukin and Hong Kong Park's group. Thank you very much.
Yeah. So, in your last TMU experiment, so what's the effect